In the last video, we talked about chunking and how bad chunks create bad AI results. But today, we go one level deeper because after chunking, something very important happens. Those chunks must be converted into something machine understands, and that something is called embeddings. If chunking defines what your AI sees, embedding defines how it understands meaning. Let's simplify this. Let's remove the complexity first because the word embedding sounds technical, but the idea behind it is actually simple. An embedding is just a numeric representation of meaning. That's all it is. Computers don't understand language the way humans do. They don't understand words, sentences, or intent directly. They only understand numbers. So, when we create embeddings, what we are really doing is taking human meaning and translating it into numbers that machine can compare. Not keywords, not hard coded rules. Meaning, think of it like assigning coordinates to ideas. Ideas that mean similar things end up placed close together. Ideas that mean different things end up far apart. So, when two pieces of text have similar intent, even if the words are different, their embeddings will look similar mathematically. And that's why AI systems can compare meaning, not just words. Similar meaning, similar numbers. Different meaning, different numbers. Now let's answer a very important question. Why do we need embeddings at all? Traditional systems compare words. They look for exact matches or maybe predefined rules. If the word match, the system works. If the wording changes, the system struggles. But AI systems work differently. AI systems don't just compare words, they compare meaning. And here's the problem: machines cannot directly compare meaning. Meaning is abstract. Computers only understand numbers. So, before an AI system can reason about language, we must convert language into something numerical. That is where embeddings come in. Embeddings convert text into vectors, numeric representation that can capture meaning. Once everything becomes numbers, the machine can measure similarity, compare intent, and find relationships between ideas. So you can think of embeddings as a bridge. One hand side, human language, on the other side, machine math. Embeddings connect the two. Imagine three sentences: cancel my subscription, stop recurring billing, I don't want to be charged again. Different words, same intent. A good embedding model places these close together in a vector space. Not because the words match, but because the meaning matches. That is the magic of embeddings. Let's connect this back to RAG. The flow looks like this: documents, chunking, embeddings, vector database. Every chunk becomes an embedding. When a user asks a question, that question also becomes an embedding. Then the vector database compare meaning, not words, and retrieves the closest results. Retrieval quality depends heavily on embedding quality. Now, let's talk about something engineers often underestimate. Not all embeddings are really good. A good embedding captures meaning accurately. It understands the context of a sentence, the intent behind it, and the relationships between concepts. That mean two pieces of text that mean the same thing, even if written differently, end up close together in a vector space. And that is exactly what we want for retrieval. But bad embeddings do the opposite. They may group unrelated ideas together, separate sentences that actually mean the same thing, or create noisy, confusing results. And this is dangerous because nothing crashes, the system still works. It just retrieves the wrong context. And when retrieval is wrong, the model still answers confidently. The model doesn't know retrieval failed. It simply reasons over whatever you give it. And that's how unreliable answers happen. Not because the model is bad, but because the embeddings didn't represent meaning well enough. Many engineers think if my model is powerful, my system will work. But in production, embedding quality often matters more than the model size. Because the model only reasons over what retrieval gives it. Wrong retrieval, wrong reasoning. Embeddings do not understand your business. This part is really important. Embeddings are trained on general language. They don't automatically understand your company terminology, internal policies, domain specific meaning. That's why chunking, metadata, and data quality still matter. Mistakes teams make, assuming all embedding models are the same, ignoring domain mismatch, choosing embeddings without testing retrieval quality, focusing only on model performance. In reality, embedding choice should be driven by how well retrieval works. Embeddings don't make AI intelligent, they make meaning searchable. Now you can see the full chain. Chunking decides knowledge boundaries, embedding represents meaning, vector databases find similarity, and RAG turns that into final answer. If you are building real AI systems, embeddings are not just technical details, they decide whether your AI understands intent or completely misses it. Good embeddings make retrieval reliable, and reliable retrieval builds trustworthy AI. In the next video, we'll go deeper into how to choose embedding models and how to measure embedding quality in real systems because that's where most production mistakes happen. Thanks for watching.